In the previous video, we talked about the integral test, using the integral test to see if a series is convergent or divergent. In this video, we're going to finish this section talking about the estimates of sums. And so the idea is that you have a series that you developed for some application in physics, engineering, chemistry, biology, business, wherever. You've got the series. Well, okay, you have a sequence, and you decide that you want to evaluate the corresponding series for that sequence, which means that you put that sequence into a summation. So now you've got this series, and if for most cases you aren't able to find the explicit S sub n formula for that series. If you have the S sub n formula, then you've pretty much you understand the series. You can take the limit of that as n goes to infinity, see what the limit is. If so, you have everything you need. But in most cases, you're not going to be able to get that S sub n formula. And so not only can you not get that S sub n formula, but you can't even find what the series is equal to. But you still have the series as far as the summation. You still have the S sub n as a summation. So there's always the option, even though you can't get the exact series sum, you could always put this sum into like a computer program and plug in n is equal to 1 million, 10 million, whatever. You know, a computer could calculate to a really high n, depending on, computers are really powerful, right? And so in a lot of situations, it's not that big of a deal if you can't get the exact sum, as long as you can get a really accurate one. Now, as you can imagine, we don't need to come up with any method for getting estimations of series. There's no method for getting the estimation for any situation. For all of these sections we're about to do, we're always starting off to where we have this, right? We're testing series to see if they're convergent or divergent. We start off, we have this already. So there's no technique for getting an estimation of a sum. The technique is you just plug in whatever n you want and do the sum. So what we're talking about, this estimates of sums here, it's not talking about, in this video, we're not talking about how to get an estimate of the sum. What we're really talking about is there a way to estimate how accurate our sum is based on the n we put in? Because it would be nice if we had this in a computer program, it would be nice to say, instead of putting in n is equal to a million or a billion, could we put in that we want the sum to be accurate to within 0.1% or 0.01% or whatever? And then it calculates the corresponding n for us. That would be nice. Okay, and so that's what we're talking about here. Okay, and so another thing to note is, before we get into this, in this section, we're going to come up with a way to calculate how accurate the estimation for our sum is, strictly in relation to a series that we analyzed using the integral test. So it's a series where, if you replace the n with x, it's positive, continuous, and decreasing. And the reason is because you can see here, we're going to be using the improper integrals. We're going to be using, if we come back here, we talked about in the previous video, we're going to be using this idea to where the improper integral, depending on how you set it up, represents a value that's less than or equal to the series sum, or greater than or equal to. And so we can apply what we're about to learn in this video to a function that couldn't, you don't have to use the integral test on that series, but the idea is you can only apply what we're about to learn to a series that would be applicable to the integral test for convergence if you wanted to use it. And remember from the previous video, the constraints for that were, in general, that if you replace the n of the sequence formula with an x, that it's continuous, positive, and decreasing for the entire range. But there was some flexibility on that we talked about in the previous video. So the idea is, again, what we're about to learn here is a way that if you're dealing with a series, if you wanted to apply the integral test for convergence to it, it would satisfy the criteria to apply that test. Then if you're going to calculate an approximate sum, just by plugging in a big N value into the summation. If you want to know how accurate that sum is, you can use this remainder estimate for the integral test. And as you can imagine, in upcoming sections with other tests for convergence that are different from the integral test, those will have their own corresponding way of quantifying the accuracy of an approximation for the sum. Okay, so it says that suppose we have been able to use the integral test to show that a series is convergent, and we wanted to find an approximation for the sum S of the series. Of course, any partial sum is an approximation to S, because the limit as n approaches infinity of S sub n is equal to S. But how good is such an approximation? To find out, we need to estimate the size of the remainder. Okay, so here's they call this the remainder. And what this means is, so we've got this infinite sum here. And so this is, we've got A1 plus A2 plus A3 plus, and then you can imagine we get to A sub n, right? We can write it this way, but then we're going to infinity. And so what we're going to do is we're going to say that then we've got A sub n plus 1 plus A sub n plus 2 plus A sub n plus 3 all the way to infinity. This is how we're going to write. We write the infinite sum. This is one way to write out the infinite sum. Okay, so this is what they're calling. This is what they're calling S. The entire infinite sum. It's not S sub n because it's not a function of n. We know it's convergent, right? We've said that this is convergent, so we know that this is equal to S. It's not S sub n. It's not a function of n. The infinite sum is just the infinite sum. All these terms summed together is S. The partial sum, S sub n, so you're summing the first n terms, is this A sub 1 plus A sub 2 plus A sub 3 all the way to A sub n. And so this is kind of confusing. It's like, are we talking about a sequence here, a series here, a number here? Well, it's the same sense of how you can think about S sub n, this S sub n. You can think about that as a sequence or a number too, right? I guess it's kind of the same thing with a regular sequence like A sub n, but like, you know, if you plug in n is equal to 50, you get a number. Same thing with a sequence, but I guess with the S sub n, this depends on how you look at it, right? It's a sequence. It's also a list of numbers you're summing. It's also a number if you plug in an n, but so, okay. If you imagine taking S minus S sub n, and again, so like, do you think about this as a number or a sequence, or, you know, in this sense, we're going to be kind of thinking about it as S is the sum of all of these terms going out to from 1 to infinity. If you subtract from that S sub n, the sum of the first n terms, then you subtract out the first n terms and you're left with A sub n plus 1 plus A sub n plus 2 plus A sub n plus 3 all the way to infinity. And that's what they're calling R sub n. And so R sub n, is it a sequence? Is it a number? It's just like S sub n. R sub n is just like S sub n. Except it's a function of n. S sub n is the sum of the first n terms. R sub n is intimately associated with an S sub n in the same sense that an S sub n is intimately associated with an A sub n. R sub n corresponds to an S sub n. It's a function of the same n. So you would plug in n is equal to 500 into S sub n, and you get the sum of the first 500 terms. If you plugged in R is equal to 500 into R sub n, that corresponds to that S sub n. It's saying what is the sum of you're starting with the 501st term, and you're going to infinity. What is that sum? You see, S sub 500 is the sum of the first 500 terms. R sub 500 with that R sub n corresponding to that S sub n is the sum of starting with the 501st term all the way to infinity. Okay, and so what we're trying to do is, in general, I mean, this setup here applies to any estimation of an infinite sum, regardless if you're referring to integral test type series. I mean, this is the general idea of what we're trying to do for any series sum, like when you're approximating it, you're trying to get a sense for how big is R sub n, in particular, how big is R sub n relative to the S sub n. And what we're going to talk about in this section is how we can get an estimation for that in relation to series that are applicable for the integral test, the integral test of convergence and divergence. Okay, and so this is done by, it says, we use the same notation and ideas as in the integral test, assuming that the function is decreasing on n to infinity. And so it doesn't have to start at 1. It's kind of like that same idea. You can do it from, if the function is only decreasing from n is equal to 50 to infinity, you can get the R sub n going from 50 to infinity and then incorporate everything else manually. It would be really easy to incorporate everything else. It's all about the infinity you're trying to deal with. Okay? But so what they do is, it's a similar idea that, okay, you've got these rectangles with base 1. And the height here is equal to it's the right endpoint. And this is we're going to have a sum of the series that's less than the area under the curve for sure. That's what the right endpoint does. And so what you end up having is the height here, the area of this rectangle, since the base is 1, with the right endpoint here, this first rectangle is a sub n plus 1, then a sub n plus 2. And so what you have is, so we're starting at, since we're dealing with R sub n, we're starting at n here. Here's n, right? We're way down the curve. We're like, this n could be 5. If this is whatever, you've calculated S sub 5,000. Now we're way down the curve. We're at n is equal to 5,000. And we're doing this right endpoint method. So with the base is equal to 1, so this is going to be 1 times the height is a sub n plus 1. So this area is a sub n plus 1, this area is a sub n plus 2, etc. Because, this is the area I'm talking about because the base is equal to 1, base times height. Well, you can see that if you take the improper integral from n to infinity of the corresponding f of x, where you replace the sequence formula, the n and the sequence formula with x, that's going to be less than a sub n plus 1 plus a sub n plus 2 plus a sub n plus 3 all the way to infinity. That's exactly what R sub n is. So R sub n is going to be less than or equal to the improper integral from n to infinity of f of x dx. So there's an upper bound on R sub n. What about a lower bound? Okay, well, what they do here is to have the areas of the rectangles be greater than the curve, you use the left endpoint. And what you can imagine is, so we've got n here, right? So this is n, okay? You could include this rectangle, and you could integrate, and so you would integrate the f of x from n to infinity, but you don't want to include this rectangle. Why? Because this is a sub n. This is not included in R sub n. So you just omit that. A sub n plus 1 starts here. So the R sub n is this would be the upper bound. Yeah, this was the lower bound of R sub n. The upper bound is on R sub n is the improper integral from n plus 1 to infinity of f of x dx. And that's it. That's the remainder estimate for the integral test. That's how you can get a upper and lower bound on the R sub n. And then from there, you can do whatever you want with it. You could subtract the upper bound from the lower bound, get a full range, divide that by the S sub n. And another way of looking at it is they take this and add S sub n to this entire inequality here, to all three portions. And so in the middle, you have R sub n plus S sub n, that's S. And so you get from that perspective, you get a upper and lower bound on the actual infinite sum, right? Once you've got this upper and lower bound on R sub n, you can do whatever you want with it. I mean, I don't know why they didn't label this like R lower and R upper, but to me, the idea would be that you would, you've got, let's say your S sub n is 5 million. You plugged in n is equal to 1,000 and you got 5 million. This is S sub 1,000. Okay. And then what I'm going to call this would be R upper. So I'm going to say R upper. No, they wouldn't call this R upper. I'm going to say that R upper is equal to this. R upper, let's say, is 100. So that's the upper bound on R sub n. And then R lower, I'm going to say, is equal to 20. That's this. So R sub n is greater than or equal to 20 and less than or equal to 100. Those are probably too small. It doesn't really matter, but let me say 1,000 and 200. Okay, so what is this telling us? What is this saying? Okay, we know for sure that the actual infinite sum, because we know there is an infinite sum. We've determined that this is convergent, that this S sub n is convergent. We know that this is less than the infinite sum, for sure, right? But so what the R sub n is telling us is it's telling us about how much less. If you add to this R 1,000, you actually get the infinite sum. So it's telling us that we're off from the infinite sum. The amount that we didn't add, that we would have needed to add to get the actual infinite sum, is it's no worse than 1,000, but it's no better than 200 off, right? It's telling us about R sub n. And so what you can think about is if you were putting into your a software code that you wanted the answer to be within a certain percentage guaranteed, then this is what's telling you this is the worst error you could have, the upper limit, right? You're not going to be any more than 1,000 off from the actual sum. So if you divide 1,000 by 5 million, then you know that that's the maximum error you're off. You could be a little bit better than that, but at worst, you're going to be that percentage off. So it would be this upper limit here that you would input into like formula for the percent error that it's for the calculation. Okay, and again, this is another way of looking at it. If you wanted to, you add S sub n to the entire inequality and you get a bound on the infinite sum. That would be like saying here that we know the infinite sum is somewhere between 5,200,000 and 5,001,000, right? We know that the actual infinite sum is somewhere between 5,001,000 and 5,200,000. That's what this is telling you. So you can analyze it from whatever angle you want. Okay, so now we're going to work some example problems, and after the example problems, you'll have a even better feel for these concepts.